Hi everybody, welcome back to the Coding and Analysis YouTube channel. And in today's video, I'm just going to do a code walkthrough of this plan that I want to do. I want to create a AVM, Automated Valuation Model. And with our sold cross-validation best boosting rounds from the previous example, I'm keeping that and I'm adding a new list of listing properties for Destin, Florida. And I think it's a list of like 300 or something like that. And I'm going to have our model determine, make a predicted sold price on those listings. Because it's like unseen data. It's like the training data that we haven't seen yet. And they're homes that are listed for sale. Haven't sold yet. So I just want to get a ballpark view of what our model would do to put down a sold price for these listings and to see how within variance or within out of variance these sold prices are going to be. So we're adding a new listing data to the cross-validation best boosting rounds example. Predict sold prices for current listings and then to determine how well our model performed on sold price predictions with the listings dataset. So we import our XGBoost from our XGBoost library and alias as XGB. Define our XGBoost hyperparameters. It'll be the XGB underscore params. We have objective regularization, or I think it's regression squared error. Specifies regression tests with a squared error loss. Learning rate is 0.1. Step size for gradient descent. Controls model learning speed. Max depth is 5. Maximum depth of each trees. So this is going to control the complexity. The subsample is 0.8. Just the fraction of samples used per tree. Attempts to prevent overfitting. The column sample by tree 0.8. Fraction of features used per tree. Adds randomness, and the seed is the random seed for reproducibility, and we leave it at 42. These are the feature columns that we're using, and they're the same as all the ones we've done before. And then here we're loading our data sets. Our DF will be our Redfin sold data, and the DF underscore test will be the new listings, our listings data set. And here we have our function, our custom function train and predict underscore CV2. So this is train our XGBoost model with cross-validation. These are our parameters, property type, features, number of folds 5. And what this is going to do is it's going to train an XGBoost regression model for a specific property type using cross-validation. And the arguments are property type and the features was the feature columns above all these, and the number of folds like I just talked about, and it's the default. The default is 5, so we'll just leave it at 5. And our data frame contains predictions on the training data, the cross-validation predictions. So the training data is basically going to be the sold prices, the training data set. We'll just call it training data set, and the listings, we'll call it the test data set. And then we use our train XGBoost model, the final model train on the full data set for the property type in the training data set. So we filter our data set to include rows of the given property type, and it's only single family. In this example, if you wanted to compare and contrast condos and townhomes, you could I guess what you could do is you go to Redfin and you could choose a city, Destin, or any city in the United States, and filter on townhomes or condos, I guess you could do single family and multifamily, something kind of similar to each other. And then if we would do that, we would get this column in the property type, and it will show the different ones. It will show the townhome and the condo. It would filter those out together. And we have our dot copy ensures a new data frame to avoid modifying the original. We don't want to modify the original, and since we have all the data right here, we won't have an error message. No data found for property type. Single family is listed for all the sold solds in the data set, and then the listings in that data set. And prepare X features. So these are the features up here that we've congregated, and the Y will be the target variable. And you can see here X equals property underscore data features. Select feature columns and fields missing values with 0, and we don't have any missing columns, so we won't have to put 0. And it's going to reset the index to ensure alignment with the target variable right here. And then we're going to add the log1p again for this exercise. So numpy, our target variable is going to be the numpy.log1p, and the price column in our property underscore data set, because we renamed the so we went from df, that was the original data set, and we renamed it to the property underscore data. So this is our copy data set, data frame that we are working on now. So that's why these are called property underscore data, and we're applying the log1p. So it's like a log parentheses 1 plus x transformation to the target variable price to stabilize the high variances due to the $1 million properties, and on the lower end it's 285,000. And then we're trying to handle our any skewed priced distributions, which is common in real estate data. And then we're setting our index of the filter data frame for consistent indexing. And here we're going to create our XGBoost D matrix. It's really an optimized data structure for XGBoost by itself. So you don't use D matrix with any other. You just use it for XGBoost alone. So now we're creating our D matrix. Then we're getting our alias XGB, and we're converting features and targets into the XGBoost D matrix formats, which is optimized for performance. So we get our feature columns in the X, and the target variable is the label, and the feature names. Feature names are included for later use in feature importance analysis. So we need the names for the feature importance, so we can know the most important columns, which ones are the most important, which ones are the least important. So when we look at the data, this is just the data inside these in the rows, and it's not really looking at the column names. So what this is doing right here is it's getting the column names for the later use in the feature importance analysis, and the label is the Y is our target variable. Now we go into our cross validation. You can see here we get our xgb.cv, and then our params parameters. We're using our xgb underscore params that we have up here at the top. So this regression task with squared error loss and all these. And then we get our D matrix that we created up here for this optimized data structure. And then Number of boosting rounds is 150. 5 is the number of folds that we're using. The metrics will be mean absolute error on log scale, and early stopping rounds is at 10, so it's going to stop training if no improvement in the MAE for 10 rounds. Then verbose evaluation suppresses detailed output during cross-validation, and then we have the 42 for reproducibility. And then when this is run, it performs a k-fold cross-validation to evaluate model performance and determine optimal number of boosting rounds. And our mean absolute error is being calculated in this log transform target, assessing prediction error. And then we get the round with the best CV score here. So we can see here index min, and then dot min right here. So we get our best number of rounds, round with the lowest test MAE, and then the best MAE is the best mean absolute error achieved. And then we're going to print it out, and it's going to identify the boosting round with the lowest mean absolute error on the test folds. And it's going to print the best, it's going to print this out in log scale with four decimal places, and it's going to show the best number of rounds was when we print out when we run our custom function. So this is going to show up first, and then we're training our final model using the best number of rounds that we determined up here in this cross-validation model performance or model evaluation. And we can see here it trains a final model XGBoost model on the full dataset for the single family property type using the optimal number of rounds from our cross-validation. So all these rounds that were determined right here, it's going to be using that. And it's on the full dataset, on the full, all the sold prices and the homes. So we're using our params again with up here all these parameters, and then we're using the matrix again and the best number of boosting rounds, the best number of rounds, and then we're predicting on the training set log scale. So we're predictions underscore log. So these are the predictions in log form. And then we're generating predictions on the training data in log scale. And right here we're making a new column called predicted price in our data frame, which is called property underscore data. And we're reversing the log1p transform and back to dollar signs. So it converts prediction back to the dollar scale, dollar size using the Pt.1 function for interpretability, so we can understand it better with the dollar signs, because we wouldn't understand the log scale, so that's why we have to reverse it, transform it back to the dollar, and then we add our data split column in our data frame. We're just going to call it CV for cross-validation. So we're adding these two columns into our data frame, and then this is how we get our feature importance analysis. We're back up here, feature underscore names. So that's why we're getting the feature names for our later analysis for the feature importance. So we're retrieving feature importance scores based on average gain of splits used each feature. And it's going to return an empty dictionary if no important scores are available. And this, we get our final model. So this is the XGBoost model trained on the full data set right here. And we're getting our dot get underscore score, and dot underscore score is a method from the XGBoost library. And then this importance type, we're going to put gain. So that's the average gain of splits using each feature. And you can see here we're converting converting our dictionary into a data frame with our key values. So the key values are the name. So that's the key, and then the importance is the values. So for example, this is the key, these are the values. So that's the importance, and then this is once it's being calculated and factored in, but we haven't got to that point yet. We just have to think of this as the key and the key value pair. So this is the key and these are the values. So let's go back up. I have some more code to get through. And then property type, which would be single family, creates a data frame for the importance dictionary, including feature names and scores. And then what I wanted to do here is I wanted for the listing, just try something new. We want to add, we want to multiply the waterfront and the square feet. So when we're doing the listings, we want to give more credence, more importance to the waterfront properties and to the larger properties. I'm thinking this will help out with the $1 million properties. So our model will understand there's the larger the square feet, then it's on a waterfront. It'll be in the same ballpark as the $1 million properties that are in these listings. So that's why I'm doubling the importance scores for waterfront and square feet. I mean, you don't have to do that, but I just wanted to try it out. This channel is just about trying different things and seeing what works and what doesn't work. We're normalizing the importance scores into percentages right here. Normalizing the importance scores to sum to 100 for easy interpretation. Right here, multiply it by 100. So it's really, I guess, the importance, the sum. We're getting the sum, and it's the total. And we're creating our new column in this importance data frame. It's going to be normalized importance, and it's going to be the importance divided by the total times 100. So all these divided by the total up here times 100, and that's where we're going to get this normalized importance right here. And then we display the feature importance results with this print function. It's going to be called feature importance, and it's going to be called boosted, I guess, to show that the waterfront and the square footage are being boosted. And then we're return the predictions on the training set plus our training model, getting our final model right here. So we're going to return a data frame with our selected columns and the addressed data split property type, our model's predictions, and the actual sold prices, so including actual and predicted prices, and the trained model. So this is the trained model right here. And then we create another function called apply. So we're applying our trained model to the new or unseen listing data. So we'll just call it apply model to new data. And these are the parameters, test data, and model and features. And I'll do that. I'll go over this in the next video. Thanks for watching. See y'all in the next video. Bye now.